At first, take my salam. Assalamu alaikum to our honorable guest and teacher and our audience. Today, I am presenting our paper. Our paper title is Tri-band Nano-Meta Absorber for Solar Energy Harvesting employed in the Optical Regime. Our authors is Johanuddin, MT Hassan Al-Karim, Sultan Mahmud, and our honorable teacher Sikdan Sanbib Islam. I am presenting on behalf of them. Our presentation outline contains introduction, literature review, problem statement, objective, methodology, unit cell design, result analysis, conclusion, and reference. In introduction, firstly, we have to know why solar energy harvesting. Solar energy harvesting is very promising in nowadays because it can meet upcoming energy demand and challenge. It is the cleanest form of all other energy sources. It is cost effective and it's also environment friendly. We know it can create many jobs to meet the alternative energy source, and it is accessible because this is an off-grid system. Our paper title contains metamaterial. That means our work is related with the metamaterial. So first we know what is metamaterial. Metamaterials are one kind of material that cannot be found in naturally. We have to make it by artificially. It has many extraordinary properties like negative index metamaterial, double negative metamaterial, left-handed metamaterial, and many other things. Metamaterial absorber are made from metamaterial. Basically, it is computer simulation based design. We can call it is nanotechnology based design. It is made for metamaterial to absorb a specific frequency range. By this metamaterial absorber, we can design many nanoscale antennas and solar absorber, photovoltaic cell, etc. Literature review. In our literature review, we have shown some literature review. In literature review, Jiufeng Chen suggested a triple band polarization sensitive microwave metamaterial absorber, which has 3 near unity peaks at 4.06 GHz, 6.73 GHz, and 9.22 GHz. A tunable two-dimensional periodic metamaterial of nano-ring pillar is presenting by using gold and silicon, where absorption is about 95% in visible and infrared region. Problem statement: metamaterial has changeable extraordinary electromagnetic properties that other material cannot be access it. We know that the absorbance of normal absorber is very low. This low efficiency can be removed by using metamaterial for solar absorber. Objective: to design a new tri-band metamaterial absorber that will operate at optical and nearly infrared region to enhance the improvement of photovoltaic system is another objective of our work. It can manipulate optical and near infrared region greatly. This is our unit cell design. This is the 3D view of our unit cell. In the left hand side, we are watching front view of our unit cell design, and this is the top view of the unit cell. This table shows the parameters of the unit cell. We are watching the length and width of this design is 1000 nanometer, and the total height of our design is 225 nanometer. It has 3 layers. The bottom layer, that means ground plane thickness, has 150 nanometer, and other 60 nanometer and 15 nanometer. And this is also other parameter of the unit cell, such as a square, side of x square, a radius of circle, etc. Methodology: first we have to elaborate which metal we we use here? We use tungsten and silicon dioxide because it has good optical properties, and it has a very, it has a it is very temperature sensing. For this, we have chosen this. We use Nicholson-Ross air equation to calculate absorption. The lessen the value of the reflectors and transmitters, then we will get better absorbance. For calculating S parameter, in unit cell we used a boundary condition under transverse electric and transverse magnetic polarization angle. For designing, we used CST Microwave Studio, and we used MATLAB for further data analysis. The main result has three unity absorbance in near infrared and optical region. In ABC, we can call the 3 peaks ABC, where A is 603.79 nanometer, B is 688.23 nanometer, and C is in infrared region 746.33 nanometer. All of the peaks is nearly unity. And this is in this graph we show the co and cross polarization. Here we get some slope in peak area. It is also some resonance frequency in peak area. This was a polarization conversion ratio. For analyzing the result, we used tungsten and copper and many other metal. By using tungsten, we get better absorption. This is also true for silicon dioxide. If we use silicon dioxide, then we'll get better absorption. By changing our resonator thickness and also dielectric thickness, we get different result. This is something slightly different from our main design. This is also true for our radius of circle. If we change the radius of our circle, then the output is slightly different from main design. In our design, if we change the polarization angle, then the absorption is something different from main absorption, and the result of the absorbance will worsen if we increase the polarization angle in TE mode. This is also same for TM mode. If we increase the polarization angle, then it will be then the absorbance will be lower. This is electric field distribution. The presence of we are watching the presence of red is very good. So presence of red is good for better absorbance. Okay, this is surface charge distribution. The more the surface density, surface current density, and the more absorption. This is the comparison table with previous work. Obviously, our work is better than previous work in every peak. In conclusion, we can say that this is a tri-band nanomaterial absorber has been designed, which is weakly dependent on polarization angle. It is a sandwich design, like tungsten, silicon dioxide, tungsten, and where the average absorption of 3 peaks is 99.99%. And finally, we can say that this is promising good absorbance in optical regime to collect solar energy. This is reference, and thank you everyone for listening me. Now I am expecting some question and suggestion from our audience. Thank you.